Welcome to The Alchemy of Waste, a journey into the transformative world of Scientia Professor Veena Sahajwalla. As your narrator, I invite you to explore the life and pioneering innovations of the woman who reimagined our relationship with the discarded. Through the lens of microrecycling science, Professor Sahajwalla looks past the surface of trash to see its molecular potential. By breaking down waste into its elemental components, she is redefining the very building blocks of our future. Turning glass, textiles, and plastics into high-performance green ceramics and metal alloys. This is more than recycling, it is a scientific revolution. Join us as we witness how one visionary is turning environmental burdens into industrial gold, proving that nothing is truly wasted. In this section, we examine the core mission of a true visionary. Professor Veena Sahajwalla, an acclaimed inventor, materials scientist, and 2025 Officer of the Order of Australia, is dedicated to eradicating the very concept of waste. By viewing discarded materials as untapped molecular resources, she fuels a global circular economy. As the founder of Smart at UNSW and pioneer of MICROfactory technology, her impact is quantifiable. Targeting 11 billion tons of global waste and already diverting over 2 million tires from Australian landfills. With over 380 peer-reviewed papers and the invention of green steel, her work proves that scientific rigor can transform environmental burdens into industrial opportunities. This is the blueprint for a world where waste no longer exists. Every revolution has a beginning. In The Genesis of Resourcefulness, we trace Professor Sahajwalla's inspiration back to the bustling streets of Mumbai. Growing up amidst a vibrant repair economy, she witnessed shoe repairers and electronics technicians breathe new life into the broken. This environment birthed a profound insight: waste is not a property, but a wasted opportunity. Every discarded object retains intrinsic molecular value. This realization drove her to choose engineering over medicine, focusing on problem-solving at the structural level of matter. By scaling the humble repair shop into a sophisticated circular microrecycling system, she bridges the gap between childhood observation and global industrial transformation, ensuring nothing is ever truly finished. Professor Sahajwalla's trajectory of scientific excellence is a global odyssey of breaking boundaries. Her path began at IIT Kanpur as the sole female student in metallurgy, graduating at the top of her class. This pursuit of knowledge crossed continents, from a master's at UBC in Canada to a PhD in high-temperature reactions at the University of Michigan. In 1992, she moved to Australia's CSIRO, applying atomic-level insights to heavy manufacturing. Finally, her leadership at UNSW Sydney since 1994 led to the 2008 establishment of the Smart Centre. This journey illustrates how a rigorous foundation in fundamental science can evolve into a world-changing legacy of industrial sustainability and academic leadership. We've all heard the mantra, reduce, reuse, recycle. But conventional recycling has hit a wall. Its like-for-like model, turning glass into glass, stumbles when faced with complex modern waste like electronics or automotive residue. Enter the fourth R, reform. This isn't just sorting, it's molecular alchemy. By looking deep into the atomic structure of waste, Professor Sahajwalla's microrecycling science breaks chemical bonds and rearranges elements to create entirely new, high-value materials. The ultimate goal? Lateral integration. We are shifting from mere waste diversion to a seamless loop where the discarded remnants of one industry become the essential manufacturing feedstocks for another. In this new paradigm, we don't just manage waste, we reform it into the future. Steelmaking has traditionally been a carbon-heavy titan, but we're witnessing a macro-scale revolution. The challenge is immense. Electric arc furnaces account for 40% of global production, traditionally fueled by non-renewable coking coal. The solution? Green steel. Through polymer injection technology, PIT, Professor Sahajwalla has turned old tires and waste plastics into a vital industrial resource. By injecting these shredded polymers into the furnace, they react to generate heat and create a stable foamy slag. This isn't just clever recycling, it drastically boosts energy efficiency, lowers costs, and diverts millions of tires from landfills. Now commercialized globally, from Thailand to Norway, this innovation proves that yesterday's waste is the literal fuel for tomorrow's heavy industry. Let's zoom in on the invisible magic making green steel a reality. At a blistering 1,500 degrees Celsius, we witness the molecular mechanics in action. Here, complex waste polymers don't just burn, they undergo rapid thermal decomposition, liberating vital carbon and hydrogen. This is where the hydrogen advantage takes center stage. Acting as a high-efficiency reducing agent, hydrogen strips oxygen from iron oxide, a transformation captured in the elegant chemical reaction. Iron oxide, i.e. rust, plus hydrogen reacts to iron plus water. By harvesting the chemistry locked inside discarded tires, we aren't just making metal, we're slashing the carbon footprint by up to 80%. It's a masterclass in elemental efficiency, proving that the solution to heavy industry's greatest challenge was hiding in our scrap heaps all along. Welcome to the operating theater of the future, materials microsurgery. Here, we move beyond simple sorting to treat waste with the precision of a surgeon. By utilizing selective thermal isolation, Professor Sahajwalla's team navigates a complex activation curve, using heat as a scalpel to trigger molecular transformations between 400 degrees Celsius and 1550 degrees Celsius. This isn't just destruction, it's synthesis. Witness a primary breakthrough, thermal nanowiring. By fusing common crushed glass with discarded tires at extreme temperatures, the Smart Center creates high-value silicon carbide nanowires. We are no longer just managing garbage, we are performing atomic-level extractions to birth the industrial materials of tomorrow, all while ensuring zero toxic emissions. This is the delicate art of giving waste a second, more brilliant life. The era of the industrial monolith is ending. We now enter the world of micro-innovation, exploring the revolutionary microfactory concept. This represents a radical paradigm shift, moving away from massive economies of scale toward focused economies of purpose. Instead of shipping waste across oceans, these modular, decentralized plants bring the solution directly to the source. Occupying as little as 50 square meters, these high-tech hubs transform problematic waste into bespoke products tailored for local community needs. By eliminating the carbon footprint of global transport and fostering regional jobs, we are building a sovereign, sustainable manufacturing capability. This is the future, small-scale, highly specialized, and deeply connected to the communities it serves. We are decentralizing the revolution. We stand at the crossroads of industrial history, witnessing the definitive transition between two ages of manufacturing. In the traditional industrial age, we relied on massive, centralized infrastructure that demanded pristine, single-stream materials and left behind a trail of high shipping emissions. But the microrecycling age offers a smarter, more agile path. By utilizing 50 square meter modular pods, we can now process complex, hazardous waste streams right where they are generated. We are moving beyond the limitations of like-for-like recycling toward lateral integration, where discarded glass and textiles merge into high-value green ceramics. This shift from a vulnerable, globalized supply chain to a localized, sovereign future ensures that waste is no longer a burden to be shipped away, but a resource to be reformed. Welcome to the era of urban mining. Our modern lives are powered by electronics, but these devices often end up as a toxic tide of e-waste. This slide reveals how we reclaim these critical materials with surgical precision. By applying precisely 900 degrees Celsius of controlled heat, we use degrading plastics to create a reducing environment, isolating rare earth elements like neodymium and dysprosium. The results are pure industrial value. High-purity alloys of copper, tin, and zinc, alongside high-grade 3D printing filaments. Most remarkably, e-waste is a richer vein than the earth itself, yielding 10 to 20 times more gold and copper per ton than natural ores. We aren't just recycling, we are harvesting the hidden treasures of the modern city. Welcome to the fusion of utility and beauty, green ceramics. In this application of microrecycling, we witness the unlikely marriage of yellowbin waste glass and discarded textiles. By subjecting these dissimilar materials to a precise heat and compression matrix, we create a high-performance surface where glass provides structural integrity and textiles offer unique aesthetics and acoustic properties. This isn't just a lab experiment. It's commercially proven, passing rigorous building codes for fire safety and slip resistance. Its real-world triumph is showcased at Mirvax Pavilion's apartments in Sydney, where it's transformed into stunning flooring, splashbacks, and furniture. We are literally building our homes out of what we once threw away, proving that sustainable design is as durable as it is beautiful. The vision now moves from the laboratory into the physical landscape of regional activation. We are witnessing a map of transformation across New South Wales. At the UNSW Sydney Genesis Hub, the foundational science is proven, but the real impact is in the field. In Cootamundra, we've seen a rapid leap from demonstration to a fully commissioned industrial microfactory. Shoalhaven scales this further, processing hundreds of tons of glass and mattresses annually, while Wellington provides circular material solutions directly to Indigenous housing projects. This ecosystem empowers local councils to shed their roles as passive waste collectors and become active, sovereign remanufacturers. We are fueling regional economies by turning local burdens into community-building resources. We celebrate a legacy defined by advocacy, accolades, and systemic leadership. Professor Sahajwalla's impact transcends the laboratory, earning her the highest honors, including the 2025 Officer of the Order of Australia and the Eureka Prize for Scientific Research. Her influence shapes national policy and strategy as a member of the Australian Climate Council and a director for circular economy innovation. As a global academic voice, she commands the world stage with prestigious international lectures. Yet her most enduring work lies in next-generation mentorship. Through the Science 50/50 initiative, she inspires young women to unite scientific innovation with environmental purpose, ensuring the green revolution is carried forward by diverse and visionary new voices. We conclude our journey with a vision of radical circularity, a definitive call to shift from the take-make-waste linear model toward a regenerative future. Professor Sahajwalla reminds us that sustainability must be the foundation of all creation, not a mere afterthought. By reimagining discarded materials as vital resources and deploying microscale innovations, we can trigger a global industrial transformation. The goal is clear: a world where waste becomes an obsolete concept, replaced by a continuous loop of innovation and purpose. As we step into this new era, we carry the understanding that through molecular science and human ingenuity, the end of one material's life is simply the beginning of another. The future isn't just recycled, it is reformed.